we will have T mapping from upper triangular matrices, 2 by 2 matrices, to upper triangular 2 by 2 matrices. So the standard basis we are using is 1 0 0 0 0 1 0 0. We cannot have 1 in the left down corner because upper triangular has 0 there. So it's only a 3-dimensional vector space with this basis. So notice that all 3 of them have zeros in the 2-1 entry because that's the lower part. An upper triangular matrix has non-zero entries only in the diagonal or in the upper left, upper right part. The T applied to an M is 8507 matrix, then M, and then the inverse 8507. So note that this is the variable M. It changes. And what we have is that this is again a linear transformation. So T is a linear transformation from the 2 by 2 upper triangular matrices onto itself. We would like to find the matrix representation. Of this transformation. So the idea is again that A is simply collecting together the images of the basis vectors. So if I denote this with E1, E2, and E3, then this is simply TE1, TE2, and TE3 collected together into a matrix. What's also important that we will need this in the S basis, the standard basis. So it's not enough that we calculate TE1. We also have to expand it in the S basis. But in any case, we have to calculate the inverse of 8507. Let me do this by hand because it turns out to be decimal numbers, but actually it might be better to use fractions. So the Gauss-Jordan elimination to get the inverse is going like this. It's already upper triangular, so we have to do the backward process. We can factor out 7, or we can divide by 7 to get 1 in the pivot here. Then subtract 5 times row 2 from the first row. We get 8, 0, 1, minus 5 over 7, and 0, 1, 0, 1 over 7. And then we divide row 1 by 8 to get the identity matrix on the left, and on the right 1 over 8 minus 5 over 56, 0, and 1 over 7. So I recommend actually that you use this fraction format, because if you use MATLAB, you might get some rounding errors when you do the calculations. So this is then the inverse of 8507. And as you see, this is also upper triangular matrix. So then to calculate T of E1, this is 8507 multiplying the 1001 0 matrix, and this is 1 over 8 minus 5 over 56, 0, and 1 over 7. Let's do first this multiplication. We get simply 1 over 8 and minus 5 over 56. The second row is 0. Then when we multiply these two vectors, we get 1 minus 5 over 7 and 0, 0. So this is T of E1, but actually what we need is the representation of this in the standard basis. That means we have to look how we can get as a linear combination of these vectors from S, the basis vectors. So the first one, we have to take ones because we have one of in the 1, 1 entry, and then in the 1, 2 entry we have minus 5 over 7, and that's supposed to multiply the second basis element. So this will be 1 minus 5 over 7, and then 0 for the third entry, the last, the 2, 2 entry. So make sure that you never use this because it's upper triangular. So actually all these entries are supposed to be 0. This is three-dimensional vector space since it's upper triangular, and only the 1, 1, 1, 2, and 2, 2 entries can be non-zeros. So that means that the coordinate matrix should have only 3 components corresponding to the non-zero components of the basis vectors. Then TE2, that's this 8507 matrix multiplying the second basis vector, which is 0, 1, 0, 0, 1 over 8 minus 5 over 56, 0, 1 over 7. Again, we do this second multiplication first. So this picks up the second row. It's 0, 1 over 7. And again, the second row is 0. And this becomes 0, 8 over 7, 0, 0. That has coordinate representation, coordinate matrix in the S basis. So we go 1, 2, and then 3, the 3 components. So this is 0, 8 over 7, and 0. And then the third one, the third basis element, and when you apply the transformation, which is a matrix multiplication 8507 times this matrix 0001 times the inverse, which is 1 over 8 minus 5 over 56, 0, and 1 over 7. So this multiplication first Again, this picks up the second row. So this is 0. No, but the first row is 0, and it picks up in the second row only 0, 1 over 7. And then the result is 0, 1, 0, 5 over 7, and 0 and 1. And then the coordinate matrix of this in the S space is 0, 5 over 7, and 1. So finally, the A matrix is all these three vectors put together into one big matrix. And the nice thing is then, if you want to apply this state transformation to any matrix, all you have to do is multiply with one matrix instead of doing a complex multiplication. So let me show you why this is nice. As an example, if you want to apply T to the matrix, I don't know, 2, 4, 7, 0, 2, 3, 4, 0, 7. If you want to apply the T matrix, so if you want to apply T transformation to the upper triangular matrix 3, 4, 0, 7, this is supposed to be 8, 5, 0, 7, 3, 4, 0, 7, 8, 5, 0, 7 inverse by definition. But then according to the new representation, we can also just use A times the representation of this matrix in the S basis, which is 1, 0, 0, minus 5 over 7, 8 over 7, 5 over 7, 0, 0, 1, multiplying the representation of this matrix is 3, 4, and 7, the three non-zero entries. And then this becomes the vector 3. Well, this becomes minus 15, 32, so that's 17, plus 35, 52 over 7, and 7. And then that means that the T transformation applied to this 3, 4, 0, 7 matrix equals to the matrix 3, 52 over 7, 0, 7. So as you see, instead of two vector multiplications or vector multiplication of three matrices altogether, we only need one matrix vector multiplication, although it's a 3 by 3 matrix times a 3 by 1 vector.